Hi class, and welcome to the review for Exam 3 Q&A. I'm going to answer some questions that people have emailed me, and I think this first question really is the most asked and also kind of addresses the most general questions people ask. But first, I want to give a little recommendation. So if you're looking for another album to listen to, an album I really like is this album called Heavy Lifter by the band. It is spelled Hovvdy, but is pronounced Howdy, like a cowboy. So this is a band, a rock duo from Austin, Texas, which is where I went to grad school, and they perform. It's rock music. It's indie rock. But I think what really hits me about this album, something about the tone of it just is exactly what I want to listen to in the morning. Like, it is morning music for me. So, it's got, catchy tunes, and it's just got a kind of light etherealness to it that feels like morning sunshine coming through a window. Okay, so let's get to question one. So this question was taken from the textbook. It's from the chapter Integrals with Trivial Integrands. So it's back in one of the earlier lectures that this exam covers. And it asks you to compute the volume of this cone first with one set of coordinates, and then changing them to a different set of coordinates. And a lot of students asked me that, how are we supposed to change coordinate systems if we're just given these sorts of inequalities? What sort of formulaic ways can we go through it? And let me outline this inequalities method that the book talks about and try to explain it a little bit better. Because the unfortunate truth is, essentially every problem you just have to figure out how to do it. And oftentimes the problems are designed so that the question they're asking can be solved, but you can't always rewrite every integral using any ordering of x, y, and z that you want to, or it might have to be split up into several different integrals depending on how you've oriented things. But for this one, first they start with kind of the way that the coordinates were given to us. So the easy coordinates to set up are to pick my volume form to be dz, dy, dx. This is the easy ordering because the z that they gave me already is in terms of x and y. So my z bounds start at 0 and go up to 1 minus square root of x squared plus y squared. This is also telling you that this curve here, this cone, a formula for it would be z equals 1 minus the square root of x squared plus y squared. And for the y coordinates, we're given that they go from minus square root of 1 minus x squared to plus square root of 1 minus x squared. And the x coordinates go from minus 1 to plus 1. Now the question asks us to change these coordinates, and the new ordering that it wants us to get them in is, and I'm going to leave myself a little bit more space to write here, dx, dy, dz. So you have to switch them so that the z is on the outside. And so the way to try to do these problems is you have a couple pieces of inequality data. So you have like these three inequalities that relate different variables to each other. And we're going to try to switch those inequalities around to understand what the bounds are for other variables. So what I mean to say is we need to get z's bounds in terms of just the constants, because it's the outermost variable in the triple integral. For y's bounds could involve z. or they could be constant, but they could. And then for x's bounds, because it's on the inside, it could involve y and z, or just y, or just z, or neither. But we know it's going to involve them. So how do we do this problem? I think it's easiest to fill them in from the outside in. So to think about the z bounds, we're iterating over this cone. And so I want to figure out what are my top z bounds and what are my bottom z bounds. And because we were given a picture of the cone, I know that I'm starting at z equals 0 and ending up here at z equals 1. So we can get those from the picture. We can also, though, get them from the inequalities. So let's try to do the inequalities in a different color. Let's do them in red. So this first inequality, like we already know z's minimum bound has to be 0, but that z's upper bound kind of depended on what x and y are. And so the way to make z as big as it ever gets in this whole cone is to try to make this 1 minus x squared plus y squared as big as it can be. So this is maximized when the square root is as small as it can be, because it's being subtracted from 1, but it's a positive number. So when square root of x squared plus y squared is minimized. And so then you ask, okay, what x and y values that are in our in the inequalities above make this as small as possible? Well, if x is 0, then the x squared portion becomes as small as possible. And the y squared would be minimized if it is also 0. And you might just want to check that y can equal 0 when x also equals 0. And so if x equals 0, that second inequality becomes y is less than or equal to minus square root of 1, greater than or equal to plus the square root of 1. So y is in between minus 1 and plus 1. So y equals 0 is in fact in our domain. So x equals 0 and y equals 0 is a valid point in the domain, which makes sense. And at that point, z is maximized. And so that's just another way of saying that this point right there is where z is maximized in the region. So our z bounds have to go from 0 to 1 because of that. Sometimes people like setting up these inequalities as saying, okay, this z inequality (1 minus x squared of x squared plus y squared) at most, so at a maximum, is 1 or 1 minus 0, right? And so the z bounds that we ended up with for the outermost integral are kind of these outermost global bounds on z. Let's now figure out the y bounds for z. So if we look at y, our first question should be, what are the global bounds on y? So similarly, we can take this inequality we were given. Y is between minus the square root of 1 minus x squared and plus the square root of 1 minus x squared, and ask what values of x minimize and maximize those two side functions. And you'll discover that we'll be at the biggest possible value to the right when x is 0, and then we're at square root of 1, which is 1. And to the left will be the smallest possible, well, there's a negative sign on there, so it's minimized when x also is equal to 0, and we're at minus 1. So y has to be in between plus 1 and minus 1 globally, which agrees with our picture, because I can see over here I'm at minus 1 in the y-axis, and, right, so I could extend this that way. And at max, I'm over here at plus 1 in our domain, so I could also read that off of there. But at a given z height, so if you're at some z here, your slice of the cone looks like a little disk, right? And so your y values on that disk are actually being determined, at the smallest and largest, by the radius of that disk. And that comes back to the cone. So in order to get our values for y, we're going to have to use, or the bounds for y, we're going to have to use the formula for the cone, which comes down to this second inequality. So let's go and solve that below. So let's just scroll. So what I like to do with this is take the inequality. So z is less than or equal to 1 minus square root of x squared plus y squared. And I want to now solve this for y, and then I'm going to let x's maximize or minimize this on the domain. So let's just first solve for y. So if I solve for y, I'm going to move the square root over to the other side. So this is the way I would do it. So x squared plus y squared. That has to be less than or equal to 1 minus z. And now I could square both sides. So 1 minus z squared is greater than or equal to x squared plus y squared. So y squared is less than or equal to 1 minus z squared, parentheses around that, 1 minus z quantity squared minus x squared. And so y is in between. Well, if I take a square root, I have to take the positive and negative square roots. So y is in between the square root, it's a pretty big square root of the negative square root of 1 minus z squared minus x squared, and the positive square root, which is 1 minus z squared minus x squared. I'm going to move that over a little bit. Okay, and now x's we don't get to control at this point, because the y bounds can only involve z. So we just ask ourselves, what value of x would minimize or maximize these two sides? And so the one that would maximize the square root on the right is if x is 0, then we're subtracting off the least amount possible, which gives me just the square root of 1 minus z squared. And over here, the same happens, but with the negative. So negative 1 minus z squared, square root, parentheses. Now, since 1 minus z, when z is in between 0 and 1, is always positive, we can cancel the square and the square root. So this is just equal to negative 1 minus z, which you could also write as z minus 1. And this right-hand side is equal to 1 minus z. And those are our bounds on y. So y is going to go between z minus 1 and 1 minus z. One thing you should maybe think about, and this will become more apparent when we do the polar solution to this problem afterward, because I think this problem is much better set up in polar coordinates, if I scroll up, is that essentially what's happening is y on this disk is maximized at the radius of the disk, and the radius of this disk at height z is 1 minus z. So r is 1 minus z. And that's pretty apparent from solving this cone equation and replacing x squared plus y squared with r squared and solving for r. But we'll come back to that when we do this in polar coordinates. So okay, and for my x bounds now, I can use the same inequality that I used to solve for y squared, but instead solve for x squared. And the reason I'm thinking about this is because I realize the x heights depend on the x values, the maximum and minimum, depend on the z height that you're at, because they also are determined by this disk. Yeah, so let's just solve for that. So if we start with the same inequality and solve for x squared, we have square root of x squared plus y squared is less than or equal to 1 minus z. And now solving for x is going to be very similar to solving for y up on the right. So we're going to end up with x squared is less than or equal to 1 minus z quantity squared minus y squared. And we can now take the inequality, or the square root. So x has to be bigger than or equal to minus the square root of quantity 1 minus z squared minus y squared, and less than or equal to plus the square root of quantity 1 minus z squared minus y squared. And since the x bounds can involve both y and z, and the y and z are specified, we're going to use those exact formulas. So you should read this, that if you fix z at a given height, so if you replace this with your radius at the height, this looks like the formulas for x, for the formulas for a disk, right? This is like the lower semicircle and the upper semicircle of the disk, or right and left, I guess, depending on, because we're in the x coordinates. But yeah, so that agrees with our sensibility. So let's just fill those in above. And my final answer for this part of the problem looks like negative square root of 1 minus z close parentheses squared minus y squared, and plus the square root of 1 minus z squared minus y squared. Let's also do this problem in polar coordinates. Okay, so let's repeat this problem, but do it in polar coordinates, or more correctly, cylindrical coordinates. So I'm going to do x and y in polar coordinates because I have rotational symmetry. Around the z-axis, but I don't have it around any other axis, so it doesn't look as spherical as it does look cylindrical. So what I'll do is re-index my coordinates. So first, just focus on the x and y coordinates for r. So if x is between -1 and +1, and y is between minus the square root of 1 minus x squared and plus the square root of 1 minus x squared, then what that's describing is a disk, is the unit disk in the xy plane. And so another way to give the description of that disk is as so the unit circle, that's radius 1, that's the y-axis, that's the x-axis. This corresponds to theta between 0 and 2 pi, and r between 0 and 1. And so when I reorient that, the only additional thing to figure out is that r squared is x squared plus y squared, so 1 minus square root of x squared plus y squared becomes 1 minus the square root of r squared, and since r is between 0 and 1, we can rewrite that as 1 minus r, because r has to be positive, so we always take the positive square root, or taking the positive square root of the square agrees with r itself. So then my last inequality now looks like 0 is less than or equal to z is less than or equal to 1 minus r, and that's maybe the other way to describe r. So it's the cylindrical coordinates, r theta, I can't remember what order these go in, never do, r theta and z, where theta is in between 0 and 2 pi, where r is in between 0 and 1, and where z is in between 0 and 1 minus r. And in those new coordinate system, the formula for the integral is much easier to compute the volume. So theta goes from 0 to 2 pi, integral of r from 0 to 1, integral of z from 0 to 1 minus r, and I have r d z dr d theta as my volume form. So let's just okay, and because there is an r in the z coordinate, in the z bounds, you're going to have to integrate the z ones before you get down to kind of simple Fubini's theorem constant bounds. So you have to do the integral for z first, plug in, and then the remaining ones are all constants, so you can do both of them at the same time or do them in either order, like with Fubini's theorem. So that's maybe a nice way to set it up. And just because we're reviewing, let's just remember that in the ZR plane, what does this cone z less than or equal to 1 minus r look like? Well, if I'm up here at 1, over here r equals 1, that's a line, and I'm only interested in this portion of the line to spin around and get the cone. And so the portion of this where r is bigger than, where r is in between 0 and 1, and z is positive, and below the graph of 1 minus r is this shaded region, which when you spin around to let theta go between 0 and 2 pi, you get the cone. So you get the region R as described above. So there you go. So that's the biggest question that I've received so far. If I get any more questions, I will try to respond to them, but I received a couple requests trying to explain how to use inequalities to set up integrals. And so hopefully this helps explain it. There were also a couple problems like this in the review that I sorted out. Yeah, so good luck. If I get more questions that I respond to, I'll make some videos and upload them later. Bye.